Hello, and welcome to the TI Precision Labs series on passive components and circuits. Today we'll be discussing the transient and frequency-based behavior of resistors, capacitors, and inductors. Before we discuss the passive electrical components, let's review complex numbers. Recall that in mathematical nomenclature, the letter I is used to represent the square root of -1. Because no such real number exists, we refer to this as an imaginary number. Also note that because I is typically used to refer to current, electrical engineers prefer to use the letter J. So any number can be expressed as the sum of its real and imaginary parts, as shown here for x equals A plus JB. In this equation, the term A is the real part of the number x, and the term B is the imaginary part. Complex numbers can also be represented by a magnitude and a phase or angle. Similarly, electrical impedances, denoted by the letter Z, can have both real and imaginary parts. The real part is called resistance and is represented by the letter R. The imaginary part is called reactance and is represented by the letter X. The magnitude and phase of a complex number can also be used when describing the impedance of a passive component. Let's now discuss the simplest of the passive components, the resistor. The ideal resistor has an impedance that is purely real. In the time domain, this behavior is defined by Ohm's law, which states that the instantaneous voltage across a resistor divided by the instantaneous current through the resistor gives the component's resistance. The voltage drop across the resistor corresponds to the direction of the current flow through the resistor. Note that the impedance of a resistor in the frequency domain is found in the same manner, as its resistance is independent of frequency. Because the voltage across a resistor and the current through a resistor are proportional, it is easy to visualize the current in time from the voltage in time, and vice versa. In other words, the plots of voltage across time and current across time will have the same shape for an ideal resistor. They will be scaled relative to each other according to the resistance of the component. Another consequence of Ohm's law is that both voltage across and current through a resistor can change instantaneously. This may not seem like a big deal, but it is actually not the case for the capacitor and the inductor. Let's now move on to the next passive component, the capacitor. The capacitor's behavior is noticeably different, as the current through the capacitor is proportional to the derivative of the voltage across the capacitor. The formula that defines the transient behavior of the ideal capacitor is written as I equals C dV over dt, where I is the current through the component in time measured in amps. C is the capacitance of the component measured in farads, and V is the voltage across the component in time measured in volts. Performing a Laplace transform gives us the impedance of the capacitor in the frequency domain. Here, Z sub C is the impedance of the capacitor in ohms. J represents the square root of -1. Omega represents the signal frequency in radians per second. And C is the component capacitance in farads. Note that the impedance of the capacitor is inversely proportional to the frequency of operation. For this reason, the behavior of the capacitor can be approximated at low and high frequencies. For example, at DC or low frequencies, the impedance of the capacitor grows, such that it can be treated as an open circuit. For very high frequencies, the impedance of the capacitor drops, such that it can be treated as a short circuit. As with resistors, the voltage drop across a capacitor corresponds to the direction of the current flow through the capacitor. As mentioned in the previous slide, the current through a capacitor is proportional to the change in voltage across the capacitor. Consequently, the plot of current versus time can be ascertained from the plot of voltage versus time. An important consequence of this relation is that it is impossible for a capacitor to experience an instantaneous voltage step across its nodes. Why? Because the derivative of a line of infinite slope is an impulse. In the case of the capacitor, an instantaneous step in voltage would require an instant of infinite current through the capacitor. Clearly, this is impossible. Thus, any change in voltage across a capacitor requires a finite amount of time to take place. So far, we have looked at the current through a capacitor given a voltage across the capacitor. But what happens to the voltage across a capacitor when it is charged with a constant current? As you can see in this plot, a constant current flowing through a capacitor results in a linear change in voltage across the capacitor. This relationship is important in op-amp design, specifically op-amp slew rate. In the videos on slew rate, you will learn that an op-amp's slew rate is determined by its Miller capacitance and the maximum current it uses to charge the capacitance. The slope of the resulting linear output is known as slew rate. We now consider the final passive component, the inductor. The inductor's transient behavior is defined by the formula V equals L di over dt, where V is the voltage across the component in time, measured in volts. L is the inductance of the component, measured in Henry, and I is the current through the component in time, measured in amps. As with the capacitor, we can use a Laplace transform to find the impedance of the inductor in the frequency domain. Here, Z sub L is the impedance of the inductor in ohms. J represents the square root of -1. Omega represents the signal frequency in radians per second, and L is the component inductance in Henry. Note that the impedance of the inductor is proportional to the frequency of operation. As with the capacitor, the behavior of the inductor can be approximated at low and high frequencies. At DC or low frequencies, the impedance of the inductor is also low, such that it can be treated as a short circuit. For very high frequencies, the impedance of the inductor rises, such that it can be treated as an open circuit. The voltage drop across the inductor corresponds to the direction of the current flow through the component. Because the voltage across an inductor is proportional to the change in current through the inductor, the plot of voltage versus time can be determined from the plot of current versus time. Also due to this relationship, it is impossible for an inductor to experience an instantaneous current step. An instantaneous step in current would require an instant of infinite voltage across the inductor. Clearly, this is not possible. Thus, any change in current through the inductor requires a finite amount of time to take place. In closing, let's consider two of the most common passive component arrangements: series impedances and parallel impedances. Two or more components are considered to be in series when they share the same current. With discrete components, this can be done intentionally. The circuit designer may choose to do this to minimize the power being consumed by each component. Series impedances may also occur parasitically. Regardless of how they occur, they can be simplified to a single equivalent component to facilitate calculations. For example, resistors in series can be simplified to a single component whose total resistance is equal to the sum of the individual resistances. Similarly, inductors in series can be simplified to a single equivalent inductor whose total inductance is equal to the sum of the individual inductances. To find the equivalent capacitance for a set of capacitors in series, sum the reciprocals of each capacitance and take the inverse. On the other hand, two or more components are considered to be in parallel when they share the same voltage drop. Again, this may occur intentionally or unintentionally, and they too can be simplified to a single equivalent component to facilitate calculations. In this case, resistors can be combined to a single equivalent component by summing the reciprocal of each resistance and taking the inverse. Since parallel resistors are quite common, it's good to know a couple of rules of thumb. For example, if two resistors of the resistance R are in parallel, then their equivalent resistance is equal to 1/2 of their individual resistance, or R over 2. Similarly, the equivalent resistance of two or more parallel resistors will always be smaller than the smallest individual resistance. An equivalent inductor for parallel inductors can be found using the same equation. To find an equivalent capacitor, simply take the sum of the individual capacitances. That concludes this lesson. Thanks for your time, and please try the quiz. Question 1. True or false? A capacitor can undergo instant step changes in voltage. The correct answer is false. Remember that the equation defining the transient behavior of a capacitor is I equals C dV over dt. Since the derivative of a step is an impulse, and a capacitor cannot pass infinite current, it is also not true that a capacitor can undergo instant step changes in voltage. Question 2. From left to right, the plots below show the impedance versus frequency relationship of which components? The correct answer is C. From left to right, the plots describe the impedance versus frequency of a capacitor, then a resistor, and finally an inductor. Remember, the capacitor has an impedance that is inversely proportional to frequency. The resistor has an impedance that is independent of frequency, and the inductor has an impedance that is proportional to frequency. Question 3. Looking in from Vin, what is the equivalent resistance of this resistor network? The correct answer is 15 kiloohms. To solve this problem, begin taking equivalent impedances from the ground node toward the input. The two 10 kiloohm resistors are in parallel and have an equivalent resistance of 5 kiloohms. This is then in series with the 5 kiloohm R5 resistor. Together, this forms a 10 kiloohm resistance. Finally, consider the resistor bridge formed by the four remaining 5 kiloohm resistors. R1 and R2 are in series and form a 10 kiloohm equivalent resistance. The same is true of R3 and R4. Taking the equivalent resistance of R1 and R2, along with R3 and R4, we have two 10 kiloohm resistors together in parallel. This leaves us with a single 5 kiloohm resistor equivalent to the combination of R1, R2, R3, and R4. This can be combined in series with the equivalent resistance formed by R5, R6, and R7, which we found to be 10 kiloohms. So overall, we have an equivalent resistance of 15 kiloohms. That's all for now. Thanks again for your time.